Hello everyone, I'm Antonio Scardace, a first-year PhD student at the University of Catania. I'm honored to be here presenting our work accepted at WACV 2026, which is titled A Novel Metric for Detecting Memorization in Generative Models for Brain MRI Synthesis. Generative models are becoming very popular in medical imaging. They are often used to generate synthetic data, for example, to increase dataset size or for disease progression modeling, where models are trained to simulate how a pathology evolves over time by generating future medical scans. However, there is a serious risk behind these approaches because recent studies have shown that generative models can memorize training data. And this means that a model can unintentionally reproduce images that are extremely similar or even identical to real patient scans during inference. In medical imaging, this is particularly dangerous because brain MRI or chest X-rays contain fine anatomical details that can uniquely identify a patient. If a model leaks this information, it can lead to privacy violations, ethical and legal issues with regulations like the European GDPR or the AI Act, and a slowdown in the adoption of artificial intelligence in clinical practice. Because of this, it is important not only to train generative models safely using techniques like differential privacy or federated learning, but also to reliably measure and detect memorization in order to certify whether a trained model can be considered safe. In the state of the art, detecting memorization is usually done in two steps. Many synthetic images from the model are first generated, and then each synthetic image is compared with the real training images using a similarity metric. In this context, the problem is that most existing similarity metrics, like the famous SSCD, are not designed for medical images and often fail to capture fine-grained anatomical details like cortical gyri, which are crucial to distinguish different patients in medical data. Additionally, classical metrics like SSIM work well for aligned images, but they are slow and very sensitive to small patient misalignments. In practice, though, medical images are not always perfectly aligned, and large-scale comparisons can involve millions of image pairs. So, we need a method that is anatomically meaningful, robust to rigid transformations, and computationally scalable. To address these limitations, we propose Deep SSIM. Our approach is based on the SSIM metric, but instead of computing it directly, that could be costly, Deep SSIM is trained to project images into a learned embedding space and ensure that the cosine similarity between embeddings matches the ground truth SSIM score. This preserves two key properties. One, the anatomical sensitivity of SSIM, and two, the efficiency and robustness of embedding-based similarity. In fact, in terms of efficiency, our proposed Deep SSIM is orders of magnitude faster than SSIM. For example, to compute millions of comparisons between real and synthetic images, it requires only a few seconds, while SSIM requires more than 30 hours. Here, we can see how Deep SSIM works. Given a pair of real and synthetic images, we first compute the ground truth SSIM score in the image space, which is used only during training as a supervision signal. Then, both images are passed through a neural network encoder. But before encoding, we apply anatomy-preserving augmentations such as random flips, rotations, and contrast changes, which are important because they make the model robust to small spatial variations. Then, the encoder maps each image to a fixed-length embedding vector, and we then compute the cosine similarity between the two embeddings. As encoder backbone, we choose a COMNEXT CNN because it is inspired by transformer design principles and is able to capture richer and more global features than the classical ResNet. The training objective is as follows. We minimize the mean squared error between the cosine similarity of the embeddings and the SSIM score computed in the image space. After training, the SSIM can estimate similarity without computing SSIM explicitly and without requiring image alignment. Once we have deep SSIM, we use it to define a memorization metric. Based on two thresholds set to 0.60 and 0.85, we classify image pairs into three categories. Different, meaning that the two images share no relevant anatomical similarity. Similar, meaning that the images are anatomically close but still show meaningful differences. And duplicate, meaning that the images are almost indistinguishable and differ only by non-semantic factors such as noise or small intensity changes. A training image is considered memorized if at least one synthetic image is classified as duplicate. In our experiments, synthetic images are generated using a latent diffusion model that has been trained under memorization-inducing conditions in order to reliably study and evaluate memorization effects. Our dataset is composed of pairs of images containing a real image from the training set and a synthetic image generated by the latent diffusion model. We evaluate deep SSIM on several experiments and compare it with state-of-the-art methods, including the original SSIM, SEM-dedupe, and recent memorization metrics proposed by Chen et al. And R et al. On perfectly aligned images, obviously SSIM performs very well. However, when small spatial misalignments are introduced, which are common in practice in medicine, its performance drops dramatically. In contrast, deep SSIM remains stable and achieves higher macroF1 scores, better class separation, which can be seen from the silhouette score, and significantly improved robustness. Even though our main experiments are on brain MRI data, we further tested generalization on chest X-ray images, which represent a different modality and anatomical region. Deep SSIM shows consistent performance, confirming that it is not limited to brain MRI. Here we show qualitative examples for both brain MRI and chest X-ray. You can see one real image and synthetic samples classified as duplicate, similar, and different, together with the similarity scores produced by each method. These examples clearly match the quantitative results and highlight how deep SSIM separates the classes more effectively than the other approaches. The figure on the left presents the distribution of similarity scores obtained by each method across the different classes. While the baseline methods struggle to distinguish between classes, our proposed approach produces well-separated score distributions. The figure on the right, instead, presents a sensitivity analysis showing that the deep SSIM remains stable even when the thresholds change. So, to recap, our key contributions are a self-supervised similarity metric for medical imaging, a robust memorization detection pipeline, and an extensive state-of-the-art evaluation on brain MRI with chest X-ray tests. Thank you very much for your time and attention. Here you can find the QR codes to our paper and a GitHub repository. Please feel free to contact me if you have any questions. I look forward to seeing you at the poster session at WACV 2026 in Tucson.